This is going to illustrate what we just talked about in the previous video, principal stresses as well as maximum in-plane shear stress. So here we're given a stress element, and it is subject to a sigma y value that is causing a tensile effect of 90 megapascals. We have a sigma x value causing a compressive effect of 20 megapascals, and then we have a shear stress that is has a magnitude of 60 megapascals that is oriented in its positive sense. So part A of this example, we want to compute the principal stresses and the orientations associated with that. And then part B, the maximum in-plane shear stress and its associated average normal stress and its orientation as well. So under the solution, what I like to do is make sure we know what values we have. We have a sigma x value of negative 20 megapascals. We have a sigma y value of positive 90 megapascals. And we have a tau xy of 60 megapascals. And all of this is based on our sign convention that we should be very familiar with from the lab sessions and mechanics of materials class. So let's jump right into part A. So part A says compute the principal stresses. So we're going to have a sigma 1 comma sigma 2 equals sigma x plus sigma y divided by 2 plus and minus the square root of sigma x minus sigma y over 2 quantity squared plus tau xy squared. All right, so there's really no trick to this. You just got to be careful with the signs, okay? So sigma 1, I'm going to go ahead and substitute these values in one at a time. I'm going to have negative 20 MPa plus 90 MPa divided by 2 plus the square root of negative 20 MPa minus 90 MPa. Again, watch your signs. Divided by 2, quantity squared, plus 60 MPa quantity squared. So you want to punch that in your calculator very carefully. When you do that, you should get a sigma 1 value of 116 megapascals. So I think you should make sure you check that and make sure you get the same number that I get for sigma 1. And then sigma 2 is going to be a similar formula but with a negative sign. So again, we got negative 20 MPa plus 90 MPa divided by 2 minus square root of negative 20 MPa minus 90 MPa divided by 2 squared plus 60 MPa squared. So notice it's pretty much the exact same term. It's just that you have a negative in front of the square root instead of the positive. So when you punch this through, I get a negative 46.4 MPa. And again, make sure you get the same number I got. So those are your principal stresses. That's it. Sigma 1 is the major principal stress, and sigma 2 is the minor principal stress. Now, here's where you do need to be careful and be cautious. Depending on if tau xy or sigma x or sigma y are positive or negative, you could end up getting a sigma, what you call sigma 1 is a smaller number than what you called sigma 2. In that case, you just relabel them, okay? So all we're saying is that the larger numerical value should be labeled sigma 1, okay? So again, if you punch these two formulas through and you happen to have numbers that sigma 2 gives you a bigger value than sigma 1, then you just flip the labels. Call the one with a bigger number sigma 1, okay? So the next part of part A is to get the orientation, all right? So for the orientation of the principal stresses, we're going to say tangent of 2 theta p equals 2 times tau xy divided by sigma x minus sigma y, okay? So here's where you got to be careful, all right? You got to be very careful. You're solving for theta p, okay? So if we substitute some values in, we get tangent of 2 theta p equals 2 times 60 megapascals. I'll write that a little nicer. Divided by, and we will have negative 20 MPa minus 90 MPa, okay? So I get tangent of 2 theta p equals, and let's punch this through together. We get 2 times 60 is 120, and then 90 and 20 together is 110. So I get a 120 divided by a negative 110. So I get negative 1.0909, so on and so on, okay? So then I want to get theta p. So theta p is going to be equal to the arc tangent of that number divided by 2, okay? So let's do that, okay? Let's punch that in and see what happens, and make sure you know if your calculator's in degrees or radians. I'm keeping mine in degrees for this. All right, and so I get a theta p value of negative 23.74 degrees here. Now, remember earlier we said that this represents actually, like, this equation represents both angles, theta p1 and theta p2, in which they are 90 degrees apart, okay? So here's what I suggest, and in mechanics of materials, we went over this. You need to call this number that you just calculated, call that either theta p1 or theta p2. It doesn't really matter. You just call it one of those two values, and then you add 90, and then you get the other value. But you have to check and make sure that you know which theta value corresponds with which sigma value, okay? Because your theta p1, whatever it is, should match with your sigma 1. And then your theta p2 should correspond with sigma 2, okay? So at this stage, I'm just going to say, let's write this down. Let's arbitrarily call theta p2. Okay, I'm just picking that, randomly, okay? And so I'm going to say theta p2 equals negative 23.74 degrees, all right? So this would mean that theta p1 equals 90 degrees plus theta p2, which is equal to 66.3 degrees, okay? So I'm not done yet. I'm almost done, but I'm not done yet. You have to ensure that your theta p1 corresponds with sigma 1 and so on. So we need to check that theta p1 corresponds to sigma 1 and theta p2 corresponds to sigma 2. Now, how do we do that? Well, in order to check that our angles are corresponding with the right stress value, we need to refer all the way back to our original stress transformation equations, okay? So we're going to say refer back to the original stress transformation equations, okay? So if you remember, we covered this several weeks ago, and it was covered in mechanics of materials. So we had this thing called sigma x prime, and that was equal to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times cosine 2 theta plus tau xy sine of 2 theta. So that formula is one that we've used before. So here's what we do. We substitute one of these theta values. It doesn't matter which one. We substitute one of these theta values, one of these theta p values into this equation along with the other sigma and tau values that we know. Now, follow me here. If we substitute theta p1, which we said is 66.3 degrees, if we substitute theta p1 into, let me make sure I did some calculations right real quick, I'm sorry. Yeah, if we substitute theta p1 into this equation, into this sigma x prime equation, and we run the calcs, we should get what number? We should end up getting the sigma 1 value from earlier. We should end up getting 116 megapascals. Now, if we don't get 116 megapascals, then what would we probably get? Well, we may get the negative 46.4, in which case what we called theta p1 is really not theta p1. It's really theta p2. Okay, so this is a way to check if our angles correspond with the correct stress value. And if it doesn't, then it's just you relabel the angle value. Okay, so here we go. We're gonna say let's plug in theta p1 and test it. Okay, let's test theta p1. Okay, so I'm gonna say sigma x prime equals negative 20 MPa plus 90 MPa divided by 2 plus negative 20 MPa minus 90 MPa divided by 2 times cosine 2 times 66.3 degrees. And then I'm going to have to wrap this equation around plus 60 MPa times sine of 2 times 66.3 degrees. Okay, so let's punch this in and see what we get when we crank all this through. So be very careful. This is obviously a lot of room for miscalculations. So I'm typing in the sine term first, and then now I'm going to go to the cosine term. Okay, now I'm going to the front term. Okay, when I punched all this through, I got 116.4 megapascals. And so that means that since, I'm going to say ... since this is 116.4 megapascals, which is sigma 1, then our angles are properly labeled. Remember I said they got to correspond. So sigma 1 equals 116.4 megapascals, which corresponds to theta p1, which was 66.3 degrees. And then you could check the other one, but the other one will work. If one of them is true, then the other one will be true. So sigma 2, we calculated that earlier. That was negative 46.4, negative 46.4 megapascals, which corresponds with, will correspond with theta P2 if you checked it. And that was, what was theta P2? Negative 23.74 degrees. I'm going to erase some of my bad scrolling. Okay, so we're almost done. We need to go ahead and sketch the transformed element. All right, so our transformed element will look kind of like this. We are going to have something like this. And I always like to draw my global axes on here just so I remember what I'm looking at. And now I'm going to put my local axes on here as well. That would be my y prime, and that would be my x prime. So, so sigma 1 is right here. That's my major principal stress, sigma 1. Here it is again, sigma 1. And then sigma 2, wrong way. Sigma 2 is in compression, right here. Right here. So then where are the angles at? Well, the angle corresponding, the angle between the x-axis, the global x-axis, and the sigma 1 vector is theta p1. So check this out. This right here is my theta p1, okay? And then the angle between the global x-axis and my sigma 2 value is right here. This is theta p2. And check it out. Look how the orientation of it is rotated clockwise, which corresponds to a negative angular value. Okay, so those are my principal stresses. Now, the second part, the part B of this problem, asked for the element with the maximum shear stress and its orientation. So we follow a very similar procedure. So I'm going to go a little faster through this because, again, mathematically, it's a very similar procedure. So we can go ahead and get tau max is equal to the square root of sigma x minus sigma y over 2 quantity squared plus tau xy squared. If we punch, there's a plus and minus in front of that square root. If we punch this through, we get plus and minus 81.4 megapascals. Okay, and then the associated average normal stress is sigma x plus sigma y over 2. Again, watch your signs here. Please watch them anywhere you're substituting them in. Punch this through. You should confirm that this is 35 megapascals. And then the orientation of it is defined by tangent of 2 theta s, which equals negative the quantity sigma x minus sigma y over 2 tau xy. So we do some rearranging, and I'm going to say let's call theta s2, similar to what we did before. So if we do some rearranging here, we'll get theta s, and solving for this, we get theta s2 equals 21.3 degrees. So theta s1 will be 90 degrees plus theta s2, which I get 111.3 degrees. So mathematically, again, very similar. I would suggest you punch this through yourself. Don't just trust me. Punch it through yourself. And again, we want to confirm that our theta s value corresponds correctly. So in order to do that, you can check the tau x prime y prime original stress transformation equation. I'm not going to show all of this because, again, like I said, it's the same general process as principal stresses. So, but you need to show it on an assignment. Okay. So once we do this, once we run these calculations, we can look at the transformed element. And the transformed element for shear stress is going to look kind of like this. And, you know, like I always like to do, I put my global axes here, okay? And then my shear stresses, my maximum shear stresses are going to be kind of like this. And then this is tau max. equaling the 81.4 megapascals. And there is an associated average normal stress, and it was a positive 35 megapascals. So that's a tensile effect. And that's actually going to be shown on all sides of the transformed element. Okay, that 35 MPa average normal stress is on all sides. Okay, now the local axes are going to stem off just like this. This would be x prime, and then this would be y prime. So where is the theta S2? Theta S2 should be right, should be right here. Theta S2, and that was what we calculated earlier, is 21.3 degrees. And then theta S1, if you swirl around right here between the global x-axis and then the local y prime axis, this right here is theta S1. Okay, so in this particular calculation for shear stress, I definitely went pretty quickly, but like I said, it's pretty much the same general mathematical process that I went into more detail with the principal stresses. Okay, so again, one thing to note back on part A with the principal stresses, notice no shear stresses here, right? We said there's no shear stresses that act on the principal stress element, okay? But there is normal stress on the maximum shear stress element. So please be mindful of that. And again, none of this should be brand new to you.